Okay, now let's do one last example of using the ratio test, looking at whether a series converges or diverges. And to blow the punchline, this series is going to be one where the test is inconclusive. So here we have the series sum n equals 1 to infinity of n squared minus 4n plus 2 divided by n to the fourth plus 6n plus 17. Now, this series here, we're going to go ahead and apply the ratio test. Right, so here the ratio test, we're going to calculate this quantity r, which is going to be the limit as n goes to infinity of, we're going to take the n plus first term, so that's going to be n plus 1 squared minus 4 times the quantity n plus 1 plus 2 divided by n plus 1 to the fourth plus 6 times n plus 1 plus 17, and then we're going to do my trick as before, divide by the reciprocal, or multiply by the reciprocal of the nth term. So that's going to give us n to the fourth plus 6n plus 17, and then we're going to divide this by n squared minus 4n plus 2. Maybe I should put some brackets in here just to make it clear what's going on. Okay, this looks abysmal, but as you presumably know, right, when we're taking a ratio of rational functions, all that matters is the dominant term on the top and the dominant term on the bottom. Right, so here we have a product. So we have the dominant term here is going to be an n squared. The dominant term here is n to the fourth. Here we're getting an n to the fourth, and here we're getting an n squared. So this is going to be equal to the limit as n goes to infinity of n to the sixth over n to the sixth. So we're going to get 1. And this is one of our inconclusive cases. This is inconclusive for the ratio test. Now, a reasonable question is to ask, what is a good test in order to deal with this problem? And here, I'm going to recommend that we use the limit comparison test instead. Now, the reason for that is that we have something that looks like a rational function, right? We have the series n equals 1 to infinity, n squared minus 4n plus 2 over n to the 4 plus 6n plus 17. Now, if we look at this, the highest order term here is n to the fourth. Here, the highest order term is, n squared in the numerator and n to the fourth in the denominator. So this whole thing is going to be more or less like 1 over n squared. So what we're going to do is, right, and that 1 over n squared, that's n squared over n to the fourth. The dominant term in the numerator divided by the dominant term in the denominator. And now if we look at this, what we're going to do is we're going to do a limit comparison with that. We're going to make a limit comparison between this guy and the 1 over n squared, and we're going to observe first that the series n equals 1 to infinity of 1 over n squared converges because it's a p-series. And it's a p-series with p strictly larger than 1, right? The p is 2 there, so that converges. Now, what we're going to get is we take the limit as n goes to infinity of our expression, right? This is going to be n squared minus 4n plus 2 divided by n to the fourth plus 6n plus 17. And we're going to divide that by 1 over n squared, which is the same as multiplying it by n squared. So this gives us the limit as n goes to infinity of n to the fourth minus 4n cubed plus 2n squared, the whole thing divided by n to the fourth plus 6n plus 17, and that limit is then 1. Now the fact that that limit is 1 means then that our series, our terrible looking series, converges if and only if the series 1 over n squared converges, which it does. So this means our series converges by the limit comparison test. Okay, so based on that example, you might very reasonably ask the question, when do I use what test? When do I use limit comparison? When do I use the ratio test? What is the correct procedure for this? I would give as a general rule of thumb that if you have a rational function, so that is something with powers of n in a numerator and something with powers of n in the denominator, I think limit comparison is probably the best move. If instead you see stuff with things that look like some constant to the power n, or something with n factorial, so like 3 to the n and n factorials and stuff like that, then I would recommend using the ratio test. And we will see in a moment that also the root test is a reasonable candidate if you see things raised to the power n.